the master class on timing constraints. We'll get started now. This class will be for 1 hour, and we'll take 5 minutes in between to talk about our new course, which we are launching also. So let's get started. We'll first get started with basic of timing constraints. We'll cover some little bit advanced concepts as well. As I understand, there are few people who would like to understand basics as well, and then we'll have some aspects which are advanced for the people who already know basics of timing constraints. So this is a short version of our full course, which is complete timing constraints, which you can check on our website www.vlsideepdive.com. So first we'll talk about what is the role of timing constraints, why timing constraints are important in chip design, in VLSI design. So basically, timing constraints are used to verify the timing parameters in the design. Okay. So you verify functionality of the design using functional verification, using simulation, using assertions, system verilog assertions. You do that. But timing of the design, whether you're meeting your setup time or your hold time, is done in STA. And one of the important input to STA is timing constraints. Timing constraints provide information like what are the clock speeds, how fast or how slow your signals are going to transition, and all these inputs is provided in the form of a file commands which are known as timing constraints. STA tool then uses these specification as an input to ensure your time design is meeting timing. Now for that, one of the important, very important information about your design is clocks. Okay, clocks are hearts of the design, digital design. In digital design, as you know, right, there are flops, and if they're not getting any clock, which is a periodic behavior on signal, then your design will never work. So one of the important thing to specify are the clocks in your design. So let's see what are those things. So most important set of constraints for your design are your timing constraints, which are clocks of the design. So how clocks are defined? Clocks specify parameters in terms of what is the operating frequency of the design, on what frequency you want your design to work, whether you want your design to work on 1 megahertz, whether you want your design to work on 1 gigahertz. You specify those using clock constraints in the design. What are the various types of clock constraints? There is create clock command by which you specify clock constraints. There is create generated clock. These two commands are used to define clock frequency, the frequency on which you'll be running your clocks. There are other commands as well, which we'll understand as we go in more detail. But basically, right, one of the most important information in your constraint file is the parameter or the parameters impacting the frequency of the design. Now, one of the important thing to understand here is you're not creating a clock here. Okay, so for example, let's say this your design, this command, these commands are just telling the information that this clock is present in your design. You are not, this command is not creating a clock in your design. What is the meaning of not creating a clock? Is that you still have to instantiate PLL in your design. You still have to instantiate clock dividers in your design. The only thing you are doing by this command is telling the STA tool that your clock, these clocks are present where in the design. Just type a message in the chat window if you are able to hear me properly. Are you guys able to hear me properly? Just type it, type a message in the chat window. Okay. So let me continue. If there are any questions, just type it in the chat window and I will try to answer those questions as we go along. So let's continue. Clocks are most important aspect of your design, as we talked about that. And these commands are not creating the clock. These are just telling your STA tool this clock is present here, but you still have to instantiate your PLLs, your clock dividers in the design. In addition to that, find your constraints, which are for interfaces, which are for the input output of your design. For example, and you have your design, and design has a boundary. So you define your constraints for the boundary of the design. So you define input delay, you define output delay, you define load, you define driving cell. That also we'll talk about as we go a little bit later in this masterclass. Now let's first understand the clock behavior in detail. Typically, what are the clock signals? The clock signals are signals which repeat themselves after a certain amount of time. These are clocks in the design which are typically generated from clock sources in the design, typically known as PLL, which will take an input signal and generate a periodic waveform in the design. Since the clock behavior is periodic, what is what are the important information about the clock? One is period of the clock, which is the time after which clock repeats its waveform. So period is, you can see this clock here, it goes high, it comes low, goes high, comes low. So it keeps repeating this behavior after a certain amount of time. Here it's repeating it after 10 units. Let's say this is nanosecond. After 10 nanosecond, same behavior is repeated, and that is what is known as period of the clock, after which it keeps repeats its behavior. Now for a clock there are two aspects and other aspects also, which is for how much time it is going to be high, which is the value 1, logic value 1, how much time it's going to be high, and for how much time it's going to be low. Both of these also are important aspect of the clock behavior, and this also you specify in your design. For how much time the clock is high divided by the total period of the clock is also something which is known as duty cycle of the clock. Duty cycle is just telling you for how much time the clock is going to be high and for how much time clock is going to be low. So important thing information to provide for a clock is what is the period of the clock and for how much time it's going to be high and for how much time it's going to be low. So let's say which command is used to specify this behavior. So the command which is used to specify this behavior is the command named create underscore clock. Okay, so the command is create underscore clock. You specify period also. There are some additional options as well, which we'll talk about in the next slide. So the command which is used to define the constraints of the clock is a command named create underscore clock. Again, I'm repeating this that this is not creating a PLL in the design. It's just telling that there is a PLL in your design or there is a clock source in the design, and that clock source you are telling this particular net or the pin in the design is the clock source. Okay, so let's see how this see the one example of this command. So this is one example of this command. You specify name of the command create underscore clock, then you're telling period, then a value. This means value period of this clock is 10, whatever your design units are. Design units come from your library, or you can have set underscore units command in your SDC file. So period, if this clock is 10 nanosecond, then you're specifying waveform. and we'll come to this option, how, what is the meaning of this option. Then you are telling, which is known as port min list, where in the design these clocks are present. So with this means that this clock, it can be one element or it can be a list more than one element. You are telling STA tool that create on these nets in the design, which is C1 and second is CK, there is a clock which has a period of 10 nanosecond and waveform of this 2-4. What is the meaning of this? We'll tell. I'll come to that. Now, what STA tool will do is, starting from here, it will basically assume there is a 10 nanosecond clock here, which is coming 10 nanosecond clock here, and it will starting from here. It will start propagating to the, for example, there is a buffer. It will propagate the clock through the buffer. There is, let's say, OR gate. It will propagate the clock. So basically, it will start propagating the clock starting from here in the design. It will start reaching to the flops. All that will happen automatically. Only thing you are doing is you're specifying this clock is present, which is a period 10, is present on C1 and CK. Now let's understand the waveform option. What is the meaning of waveform? So waveform typically is a list of even numbers. Even numbers means there are total even numbers in this. So in this case, there are total two numbers. First number tells with respect to time 0 at what time clock rises, and second number tells with respect to time 0 at what time clock falls. So 2-4 means clock rises at 2 and then falls at 4. So clock has a period 10, starts from 0, it rises at 2, then falls at 4, and then 10, right? So this is the clock. Now, since clock is periodic, this thing will keep repeating. So it basically will rise now. This rises at 2, so it will rise again at 12, then fall at 14, 20. So this will keep repeating. So waveform option tells when clock rises and when clock falls. So here it rises at 2 and falls at 4. If this value was, let's say, 0, 5, that means clock rises at t equal to 0 and falls at t equal to 5. So the clock would have been like this, rises at t equal to 0, falls at t equal to 5, and then again rises at t equal to 10 because the clock period is 10. So this is how you define a clock using a create underscore clock command. You give period option, you give waveform option. Waveform option is optional. If you don't give waveform option, tool will pick like this waveform. Then you tell on which nets in the design this clock has to be created. So you are telling create this clock on net C1 and CK. It can be net or port. So C1 is internal net in the design and CK is a port in the design. You can specify clock on one element. You can specify on more than one element. Both are allowed. So this is how you tell STA clock, how a clock has to be defined. Of course, I'm not going into detail of all the options. If you want to understand details of all these options, as in we have a course available on our website, which is goes into each and every option of the constraints. So now, as I told you, right, the waveform option has even number of values. What if you have a clock? What if you give 4 values here? What is the meaning of that is clock has a period of 20. So from here to here, it is 20. It rises at 2. So basically it rises at 2 here. Then it falls at 4. Then rises at 12 again and falls at 14. So within a 20 period, there are two pulses, rises at 2, falls at 4, rises at 12, and falls at 14. This is not a usual clock. Typically, you will have rise and fall only once in the clock period, but command also allows you to create some special cases clock if you want to do that, like in this case. So let's continue. So this is how you define the clock, and you can have more than two element in the waveform as well. Now, typically, sometimes users also create a clock which is known as virtual clock. So far, the clocks we have created, you are telling on which design element that clock has to be created. You are telling, okay, this clock has to be created on C1 and CKNet. But you can have clock being created where no design element or design object is specified. When design object is not specified, this is known as virtual clock. Why would you use virtual clock? This will become a little bit more clear when we talk about input delays. But think about this, that virtual clocks are used to define input delay. So let me give you an example. Okay. Let's say you have this design, and this is the port of the design. And this port in the top level chip level design is driven from another flop. And you have same clock coming here. This clock also goes through different logic and comes here. So this clock is also coming on this port. Let's call this CLK. Let's call this CLK. Okay. Now this clock, as you know, right? When clock propagates in the design, it will have different delays. So when it propagates here, let's say it has 5 nanosecond delay in this path. And let's say when it propagates here, let's say it has 15 nanosecond delay in this path. Now, when you're doing STA of this block, what you want to do is when you at this level, you will have to tell, and we'll talk about this a little bit later, is what is the delay of this logic. Okay. So the delay, let's say delay of this logic is 10 nanosecond, but delays are specified with respect to clock. So this delay of 10 nanosecond is with respect to the clock net, which was coming here. Let's say call this net as X, and let's say call this net as Y. This delay is with respect to net X. Now in this design, let's say call this B and call this A, net X does not exist, right? So even when you define an input delay of 10 nanosecond, there is no way for you to define that it is with respect to the clock delay, which is 5 nanosecond on net X. Since you cannot define that, in order to define that, tool allows you to create, which is virtual clock. Let's say you can create a virtual clock, V underscore CLK, which is on not on any net in this design, but you're assuming in your head that this is kind of clock X, which was there. And now, with respect to this virtual clock, you can define an input delay on this design. So I understand if you are new to constraints, this concept can be a little bit complex. So at a high level, you can think of that virtual clocks are typically used to create input and output delays, so that you can have different clock delays on the clock which is present in the design, which is this case, and the clock which is outside the design. So typically these are used to define input and output delays. And we'll talk about what are the input and output delays. Now there is a special command called create generated clock command. Okay. Now typically a question which is asked is, if there is already a create clock command, why do even I need a create generated clock command? So what create generated clock command does is it allows you to create either a divided version or a multiplied version or a modified version of the original clock. Again, this command is just telling your STA tool that there is this modified version of original clock, but it's not creating the clock structure. Clock divider, you still have to instantiate in the design. Clock or multiplier, you still have to instantiate in the design. It's just telling the STA tool this kind of modified version exists in the design. So let's understand this particular clock. Typically, create generated clock, either you will define on clock dividers, which is basically dividing is if you give q bar back to d, that creates a divide by 2 version of the clock. So frequency is divided by 2. Other places you will define generated clock is clock gating. Typically, clock gating will modify, for example, let's say you have this clock and clock gating depending upon enable will, let's say, modify the clock to this. So it's modifying the original clock waveform, and then clock gating is another place you will define the clock. Why not just create this clock yourself separately, and why have create generated clock? Because it makes it easier to write the constraints. For example, let's say you're doing STA right now at 10 nanosecond, which is a source clock, and then the divided clock is basically you're dividing the frequency, so the period will be 20 nanosecond. Then you modify this to, let's say, 5 nanosecond. This will automatically modify to 10 nanosecond. You don't have to modify each period separately. Create generated clock command allows, because it's dependent upon parent period, to do that automatically, and that's one of the reason why would use create generated clock command rather than defining the primary clock itself. So these are the various options of the generated clock. The command name is create underscore generated underscore clock command. The name, you specify the name, source. We won't go into details of each and every option, but let's take an example and see how to define it. So here what I'm creating is creating using the create underscore generated underscore clock command to create a generated clock. Okay, so that's the command name is create underscore generated underscore clock. It's a divided clock, divide by 2. Keep in mind, this is dividing the frequency. This is not dividing the period. This is dividing the frequency. So if master clock has 10 nanosecond, you divide the frequency by 2, your period will actually become double. So dividing the frequency, you're not dividing the period. Okay, keep that in mind. So this clock is divided by 2. That means if your master clock had 10 nanosecond period, divided clock will have 20 nanosecond period. Okay, so this was, let's say, the master clock. So divided version will be this, which is double of that. Now you tell the source of the clock. What is the meaning of sources? Where the parent clock was there. So let's say you have this clock dividers, but the parent clock was coming from here. So source is the parent clock, where parent clock comes, which is, and it's a net in the design. It's not the name of the clock. It's the net in the design. Master clock is the name of the parent clock, which you had defined the name in create underscore clock command. And then you define the nets where you are creating this generated clock. So the nets on which I'm creating this generated clock can be more than one, or it can be one. Here I'm creating generated clock on net GC1 and GC2 in the design. So what I'm saying is on GC1 and GC2, from C1 a clock comes, and that clock frequency is divided by 2 on GC1 and GC2. So starting from GC1 net, from GC2 net, STA tool will start propagating the divided clock. So this is how you define the generated clock. Now, what can happen is typically you would see some specific options master clock, and hyphen add option. Why those options are needed? This example shows that. For example, let's say you have a multiplexer in the design. A multiplexer will call two clocks, let's say, are coming to the input C1 and C2. This C1 and C2 will propagate in the design, right? And let's say this is a clock divider and it is creating generated clock. Now, let's say C1 is, let's say, 10 nanosecond and C2 is, let's say, 30 nanosecond period. Now, there are two clocks which are coming. Now, divided version of that will be, let's say, divide by 2 is being done. So, divided version will be 20 nanosecond and 30 nanosecond divided version will be 60 nanosecond. Now, on this net, there are two possible clock period which are possible, right? One is 20 nanosecond, another is 60 nanosecond. One is divided version of C1, another is divided version of C2. So how do you define two clocks? So the way to define that is you can do create generated clock and you choose a master clock. This means that the creative clock I'm creating has master clock, parent clock C1. So the one will be divided by version of C1. And for the other, you specify master clock as C2. But you're defining the clock on the same net, which is FF2 output. When you want to define clock on the same net, more than one clock, you have to use what is an option known as hyphen add option. So you're basically creating more than one clock on the same net in the design, different master clock because their periods are different. And since you're creating on the same net, you use hyphen add option. So similarly, there is a command called set underscore clock underscore groups command. But before we go into that command, I'll take a 1 minute pause from timing constraints. Please type in your questions if you have any questions in the chat window. I also gonna talk about one of the important training program which we are launching. So let me unshare this constraint slide and share something else which we are launching now, a new kind of training program. And let me talk about that. Let me bring that up. The presentation. Let me share my screen. Okay. It should be coming up. So launching a new training program, which is a 12 weeks training program. We're launching this program with Safal. Safal is a Karnataka government incubator for semiconductor fabless ecosystem. Now, what this program has four parts. It starts with basics of VLSI, goes into specialization in one particular field. You work on industry project, and then we help you in the interviews and getting a job. It's a 12-week training program, so it's all approximately 3 months. This program starts on 3rd of April, which aligns with basically your academic calendar. In this program, we are going to use industry standard commercial EDA tools from Synopsys and Mentor, which is Siemens. You will have 24/7 access on cloud-based labs. We'll use AWS for the cloud, and you will have commercial tools access. They'll be easy to understand lecture videos. There'll be hands-on interactive sessions. So it's virtual plus physical. You will have Q&A session for multiple hours each and every day. So you will have access to the instructor. It comprehensive covers all the aspects of VLSI, starting from fundamentals to advanced. There is labs for each and every concept. There is also a special thing which we are doing is there'll be a weekly physical interaction with the industry leader. So this interaction is not with your mentors or your teachers, but with industry leaders, people from multiple product companies like Qualcomm, like Nvidia, Google, Synopsys. They'll be coming, they'll be talking about what their company is doing. They'll be also talking about what is the program going to be, how you can get job in VLSI, and that will happen every Saturday during the duration of this program, HSR layout office. This unique program which we have has been vetted by multiple, as in we have got the detailed review of this program done by multiple customers, multiple companies. For example, Nvidia, Google, as I talked about, MediaTek, Intel. And in this program, we are going to provide you 100% job assistance and assurance. And this is a unique program with hybrid live Q&A. There is an industry standard labs and projects which are vetted by our partners. This The way we are going to train you is when you get trained in this 12-week program, it will be like equivalent of working 1 year in the industries, or for some people who are doing well, equivalent to working 2 years in the industry, because we are going to make you work on real projects from these product companies. Of course, we are going to help you with mock interview preparation. We'll do your soft skills training. We'll do industry standard projects with protocols. You at the end of the basically training, you will actually develop a mini SOC, a small SOC. So if you want to know more about this program, I'll be one of the instructor for the program. I'm IIT Delhi graduate, more than 20 years in experience in semiconductor and VLSI. Of course, I founded VLSI Deep Dive. We'll have Anand who will be taking the courses on DV side. I'll be taking courses on RTL design and STA side, timing constraint side. So if you want to know more details about this program, go to our website www.vlsideepdive.com. There is a link there. You can fill a form. You'll get all the details, brochure, what kind of certificate you will get, what kind of jobs you can expect. You will get all that information from our website. Just go to www.vlsideepdive.com and there'll be a page there. Click there to click in the form. You fill the form, you'll get all the information. So this is something which is coming up. Don't miss it if you are looking someone who is graduating or looking for jobs around this VLSI area. And let me come back now to our webinar, which we were continuing, the timing constraints webinar. So let's now go more details in other commands of timing constraints. What we'll do is we'll start with what is known as set clock groups. So let me share my screen again. So what is set clock groups? In a design, you can have multiple clocks in the design. Some clocks may be synchronous to each other, meaning that STA has to time paths between those clocks. Some clocks would be asynchronous to each other. That means STA does not have to time path between those clocks. So by default, every clock in the design is synchronous. Okay. So all the clocks in the design by default are synchronous in the design, but you can change the default behavior by using what is known as set underscore clock underscore groups command. When you give asynchronous option, that means you are telling that clocks are asynchronous to each other. And then you can give multiple groups. What is the meaning of these groups is you can specify multiple clocks in each of those groups. One clock can be present only in one group. What this command means is you are telling relationship among the groups. So this command is telling this clock group set and this clock set are asynchronous to each other, but no relation is implied within a group. You are not getting any. This command does not say because these clocks are in same group. This is not implying any relationship between clock 1, clock 2, and clock 3. The only thing it is saying is this group and this group are asynchronous to the each other. What this means is clock 1 is asynchronous to clock 4, clock 5, clock 6. Clock 2 is asynchronous to clock 4, clock 5, clock 6. Clock 3 is asynchronous to clock 4, clock 5, clock 6. But no relation can be assumed among clock 1, clock 2, clock 3, clock 4, clock 5, clock 6. This command is not telling that there is any relationship between these clocks. It is only telling relationship from one group to another. And that is usually a common misconception. So be aware of that. By default, every clock is synchronous in the design, unless you tell using this command, these are asynchronous. And this command tells relationship between the groups, this group and this group. Nothing is implied within the same group. Okay. So of course, I'm not going into detail of each and every command option of this, but I'm giving you an idea about what this command does. Let's understand what are the other commands in SDC or timing constraints. Another command which is input delay or port delays. So what happens is, let's say you're trying to sign off STA on this block B2. Now on this B2, there'll be, this is an input. In when you're doing at a full chip level, when data is launched, there'll be some delay on this path. Let's say that delay is 10 nanosecond. Now, when you're timing at this level, how do you specify that delay? This is specified using on the input port using a command known as set underscore input underscore delay. Using this command, what you are telling, what is the delay on the outside logic which is driving this port? So let's say this delay is 10 nanosecond, then you'll say that this input delay value is 10 nanoseconds. So using input delay, when you're timing at a lower level, you're telling the delay of the outside part of the logic, and that is what you're specifying using this command. Why it is important, we'll see one example of budgeting, and there I'll explain how this command becomes important. So input delay has multiple options. You can have clock name, you can have whether it's on the falling edge of the clock, whether it's on the rising edge of the clock. We're not going into detail of each of these options. You can go to our full course if you're interested in that. Now, one more important aspect of timing constraints is specification of path. This is important both from specifying certain commands like false path, multi-cycle paths. This is also important from the point of view sometimes when you want to do timing check on those paths, like report timing in prime time. So you have, it's important to specify paths. But before we go into details of paths, let's talk about what are the multiple options by which you can specify the path. So there are typically three options: from, through, and to. Froms mean start of the path. This is typically either a clock, a primary input port, or a sequential. Okay, so from option is for the start of the path. Through option is whatever the nets in the design path goes through. For example, this can be a net in the design. And to option is for end of the path. Again, end can be a clock, a primary output port, or a flop, or a sequential cell. So three options are used to specify a path: from, through, and to. Let's look at some examples to understand that. From can be a clock pin or an input port, or a flop clock pin. So let's say from 1CK. So let's say you specify the path from F1CK, which is basically clock pin of a flop. So this is the flop F1 and its CK pin. Typically, path starts from CK pin because you have to take into account CK to Q delay as well. So from typically start from this. So from CK means all the paths which are starting at this flop. So let's see what all the paths are there, which is starting at this flop. So there is this path, which goes through A pin of this U cell, then goes through this inverter and goes here. So this is one of the path which is starting from CK. Let's see another path, same path which comes from A, go to Z and goes to this flow. And then there is another path which comes here but goes to this flow. This path is not from F1CK because it starts at F2. So there are three paths starting from F1CK, which we have highlighted in red here. So this is how you can use multiple options from, through, to specify your paths. So this is, we understood what is a from option. Let's understand what is a to option. So let's say you say to F4D. Typically, two option would be output port, clock, or a flop deepen. So let's say you're saying to F4D. So F4 is this, and you're saying to F4D. To deepen, let's see what are the paths. There is this path. There is also this path. So there are two paths to basically F4D. So basically all the paths ending on F4D are those. So this is specifying two paths. Two F4D means even though you have used one net, means two of these paths highlighted in red. Now let's understand through option. Through option is typically used for design nets, and it's basically path goes through this, the English literal word of through. So you're saying U1A, path through U1A. So this is a U1 cell and A pin. So all the paths which go through this is U1A path. So this is one path which goes through this. This is another path which goes through this. This path is not through U1A because it goes through B pin of U. It is not U1A path. Okay. Not through U1A path. So again, here we see two paths which go through U1A. Through option can be used multiple times. Sometimes you want to really fine tune the path. For example, you want to say a path which first goes through here and then here. So you can use through multiple times. So this means through U1A, through U3O. This is an ordered. That means path first goes through U1A, which is this pin, and then goes through U3O, which is this pin. So this path first goes through U1A and then goes through U3O. This path is what is goes through first U1A and U3O. This is an ordered option, and this is how you can use multiple through option to specify a path. If, if anyone has questions, yourself on mute.
In in previous slide, you showed
If you have
path
any,
through
please
U1.
ask in the chat window. If anyone has questions, please ask in the chat window. So this command can be used to specify false path. Set false path, you can use from option, to option, through option. To say false path command means that's on certain paths in the design, you don't need to meet timing. These path specification option you can use to specify what is a command which is known as set multi-cycle path, which means that rather than timing the timing in a single cycle, you have to meet the timing in more than 7 cycles. If anyone has questions, please type it in the chat window, and I will try to answer that question when I'm done with the slides. So set multi-cycle path command can be used to specify more than one cycle for a particular path. For all these commands, set false path, set multi-cycle path can be provided using the from, to, through option that we have just discussed in terms of path specification. So now we'll also talk about one of the important aspect of constraints, right, which is known as budgeting. Typically, when you're designing or when you're signing off on a design, typically when then there are big SOCs or big chips, There are multiple partitions or multiple blocks in that chip. Okay. And sometimes it becomes difficult to do timing of this together. Of course, for final sign off, you have to do, but the runtimes can be more. It may be more productive to do timing of each of these blocks separately than doing every time all the chip together. Okay. So typically in hierarchical design methodology, budgeting can be done. What is a budgeting? Budgeting means you will let's say this is partition P1, this is partition P2, this is partition P3. You will generate SDC time constraints or timing constraints for each of these partition so that these partitions can implement or you do ST of these partition independently. In general, good budgeting means that you will generate constraints with good quality, with high reliable delay values, no over constraining or under constraining. But that's an ideal case. Typically, as in there are some limitations in terms of what you can do in budgeting. But if you're able to generate good enough STC, each of these blocks or partition you can time, optimize, run STA independently, and basically that is something you can do. Now, if you have good SDC, it achieves good implementation of these blocks and allows you to catch these issues in the SDC earlier or in your timing earlier. So we'll take one or two examples of how to do it. Okay. So basically, what budgeting is the process of distributing. Let's say you are doing two blocks. What path of the delays should be here? What delays should be here? So budgeter determines what are the input output delays by analyzing what are the delays in the logic, what are the delays in the interconnect, and accordingly generate a right set of constraints or SDC files for block A and block B. Budgeter does not modify the timing, but it only distributes slacks among these blocks. So let's take one example and understand that. Okay. So let's say you have this chip. Okay, this is full chip. The timing constraints for this chip is that you have a clock of period 20 nanosecond here on C1. There is an input delay of 3 on P1, and then there is output delay of 3 nanosecond on O1. So that means outside this, there is 3 nanosecond delay. Outside this, there is 3 nanosecond delay. But so that means within this clock, okay, clock is 20 nanoseconds. So within this, 3 goes outside, 20 minus 3 minus 3. That means 40 nanosecond time you have within this block because the clock period is 20 nanosecond. Now let us assume, I'm assuming certain things. I will assume delay of each of these wire is 1 nanosecond. So which I marked in red, whatever I'm assuming. Let's say for this block, there is combinational this delay is 4 nanosecond and this delay is 1 nanosecond. I'm assuming this is an approximation. Now what I want to do is I have these chip constraints. I want to generate timing constraints for each of these blocks, block B1, block B2, and block B3. And generating this timing constraint for each of these blocks is something which is known as budgeting. And why I want to do that is I will generate timing constraints for each of those, run the STA or PNR of that independently. And then let's say if there are fixes required, I can do much faster when I'm running it at B1 level or B2 level because these are smaller design. And so typically tools, ADA tools will run faster on smaller designs. Once I'm done with that, with the to a reasonable satisfaction level, then I will do a full chip again. Of course, as a nice final sign off, I still have to do full chip level. But running at B1 level, running at B2 level, running at B3 level, we allows me to do faster iterations. But in order to do that, I have to generate separate constraint file for B1, B2, B3, and I may not have that initially. And I generate that what is a process known as budgeting. Typically, this process is now done automatically by the tool. but we should understand the concept of how it is done. So let's first generate constraints for this block B1. Okay. So for B1, there is a flop here. What I have to do is I have to define clocks. So clock will be same, create clock period. But I have to figure out what input and output delay values I will use for this clock. Let's say at P1, 3 nanosecond delay is outside. Then this wire has 1 nanosecond delay. So outside this P1, there is 4 nanosecond delay, 3 nanosecond delay outside the chip. So let me use a different color. So 3 nanosecond delay here and 1 nanosecond delay here. So outside the chip on this port, there is 4 nanosecond delay, 3 plus 1, 4. So I will specify input delay of 4 on P1. Now let's say what output delay I will specify on O1, which is output port. So 1 nanosecond delay here. Then I assume this is 4, that means 5 nanosecond delay. Okay. Then 1 nanosecond delay here, 6. Okay. So here, from here, 6 here, and then inside that, I'll also have 11 nanosecond delay. So outside this, from here to here, starting from O1, 1 nanosecond here, 4 nanosecond here, that means 5, 1 nanosecond here again, 6, and then 11 nanosecond here, that means 17. So I will define an output delay of 17 on this output port. How did I come to this? This whole thing, 1 nanosecond here, 4 here, 1 again here, and 11 here. That means there is 17 nanosecond delay outside. So I will define output delay of 7 nanosecond. So now this has created an SDC for B1 post budgeting. Let me now create the same thing for B2. So here to create that, for this, I have to see what is the delay outside. So let's calculate that. There is 1 nanosecond delay here and 3 nanosecond delay here. So that means total of 4. So input delay here becomes 4. And let's see what is the delay here. There is 1 nanosecond delay here and there is 11 nanosecond delay here. So total becomes 12. And I will write that, and that becomes your 12 nanosecond delay. Similarly, I will do it for B3. So there is 1 nanosecond delay here and 3 here. So that means 4. And then there is 11 here, but rest is outside, which is 1, 4, 6, and 3, 9. And that is how it created. So there is a question. Why don't you, does B2 post budgeting require? B2 also you need to, if you're running B2 independently, then also, yeah, B2 budgeting is also required. There's a question, why don't you count the 16 nanosecond and 1 nanosecond for output delay for P1? P1 is input port. So on input port, input delay will be specified. So I don't understand the question. Why don't you count the 16 and 1 nanosecond for set output delay on P1? P1 is everywhere. P1 is an input port. Okay. So for P1, you will calculate input delay. What is input delay? Input delay is the delay of the outside logic. Okay. So let me clean this and let me explain again. Just a minute. Let me bring up the slide again. Let's calculate this again. Okay. So let's say you have this port. Oops. Let me share the screen again. I think it's not shared. Just a minute. So let me explain this again for one of the input port P1. Okay. So input delay on a port for B1, let's say this is the port. This is the port we are talking about. What is input delay? The delay outside this particular block B1. What is the delay outside? There is 1 nanosecond here And from here, outside here, this is 3 nanosecond. So 1 nanosecond of this interconnect and 3 nanosecond of outside the chip. So total becomes 4 nanosecond. And that is what we are defining as an input delay for viewer. Okay. So I hope this you understand now. Okay. So this process is known as budgeting or timing budgeting the timing constraint. So this covers today's session at a high level. We wanted to cover basically various aspects of time constraints. One of the important aspect is clock. How do you define clocks? And then other important aspect is budgeting, which we also covered. This we do have a full course on timing constraints, which is around 4 hour course, which covers all these aspects in a lot of detail. If you are interested, you can search for that on our website, www.vlsideepdive.com. The whole session was being recorded, so we'll put it on YouTube so that you can anytime watch it later as well. And as I talked about, right, we do have a 12-month training program which is coming up. Please go to our website www.vlsideepdive.com. You will see a link for 12-week training program. Fill in your details there and we'll get back to you. This is a commercial program, commercial tools you will be using, and it's a job assurance and guarantee program. So please go if you're interested in looking for a job. Go through this 12-week training program in VLSI, and then basically we'll get back to you. So thank you everyone for attending. The session is over. We'll also be doing another session next week in general on VLSI and careers. Please do join that session as well.